Alright, so starting off by just showing you exactly what the project is. The statistical analysis part is actually. It says in analyzing the parameters of the samples collected, a one-way analysis of variance was done using a statistical package system software. IBM is 27 experiences afterward. The kind of multiple rank test was conducted to identify significant variations at P value, which is less than 0.005, and to explore a relationship between the analyzed heavy metals and the aquatic organisms. Then a Pearson correlation analysis was conducted. So this was all. This is the whole summary of the whole system statistical package that was done. The first part is that the analysis that was done was a one-way ANOVA, and in one-way ANOVA, it show the define the main indicators used is the talk key, but you don't need that anyway. So, but what we talked about next is that after a one-way ANOVA, different multiple ring test, which is also in one-way ANOVA, was conducted to identify significant variations. So visually, the one-way ANOVA is to give you a descriptive statistics. Then the multiple multiple ring test is to be able to explain where the significance lies, and then in getting the relationship between that in analyzing the heavy metals across with the organisms, a Pearson correlation, that is correlation analysis, was conducted. So starting from the first table, if you're looking at what you're looking at right here is heavy metals in the water sample, and you have it as the mean and the standard error at each spot. So this is how you explain this table. You explain it horizontally because you are explaining each heavy metals across the three locations. Don't forget the heavy metals across three locations. And then same thing goes for the water at the same time. The parameters of the water used to be explained across the three locations. When we get there, I'll just show you also. So here you see, if you go in, okay, you see the Duquesne. Duquesne is being frequently used to represent, is being represented using the alphabet. Before it was asterisk, I put it over. So now you have it. If you want to explain like across the three locations, you have A in Sogoro, B in Makoko, and B in Ebute. What this is telling you is that there's a similarities between Makoko and Ebute. That is, the concentrations of Nike across the three locations is similar in Makoko and Ebute, while it's quite different in Sogoro. That is, Sogoro is different from the three of them. So the same thing applicable to chromium, lead, and all that. Then let me just go to arsenic. Arsenic, as Shogoro, we're having it as AB, Makoko A, Ebute B. What is this telling you is that Shogoro have similarities of arsenic heavy metal with Makoko, and also have the same similarities with that of Ebute. Alright, but Makoko and Ebute are different from one another. That is, the concentrations level of arsenic in Makoko and Ebute is different. So that is how you explain Decan significance level. So this is the graph for the water, graph for the sediment. Then I can put this graph for the concentrations of waters and sediment. This one I'm using to show you is different from the one I gave you actually. This one is the whole details and the informations of everything. So now this is the water parameters, monitored mean standards error values of water quality parameters in all locations. Now if you want to explain this one, don't forget I told you that you explain in respect to the locations. You explain the parameters or the heavy meters in respect to the location. So here right now, if you want to explain this, it's going to be vertical because the locations are in the vertical axis. So you look at the concentrations of temperature, the temperature of the water across the three locations. Is it the same? If you're looking at it closely, Suguru and Makoko tend to have a similarity, that is AA. But to Ebute is quite different from the two of them. So there is no similarities of water temperatures in Ebute across the other locations. But there is similarities of temperature in Suguru and Makoko. So that's how you explain that. Now let me just quickly go fast to oxygen dissolved. You have AB in Suguru, B in Makoko, and A in Ebute. What this is telling you is that there is a similarities of oxygen dissolved, or the amount of oxygen dissolved in Suguru and Ebute, while there is a similarities of that of Suguru and then Makoko, but it's quite different between Makoko and Ebute. So that was what decaying is all explaining. So that's how you discussed your significant difference using decaying. Now, moving fast to the concentrations. Here in the concentrations of heavy metals, these are just a simple the concentrations, the converted values. This is how the concentration. This one is showing the concentrations of in parts per million. Of course, you know that already. So now descriptive statistics of the mean concentrations of heavy metals in the waters and sediments. So this one is a summary of the water and the sediment concentrations too, because the reason why we need this table is for us to be able to calculate, to do bio accumulations. So if you want to do bio accumulations, if you look at the amount of organisms that you are analyzing, there are over 30 organisms, and the water parameters, the way to divide the matrix, the way to divide to calculate the amount by accumulating the amount the fish has taken from water and the amount the fish has taken from the sediment. We need to divide the matrix. We need to divide the amounts accumulated in the organisms by the matrix. So that means the water be divided by the concentrations of the fish, the amount of heavy metal found in the fish, and the amounts in the sediments too will also be used to divide the amount found in each fish, actually in each fish. So what I make it is to get the mean first, the mean for the water, the mean for the sediments, at the mean for Nike in across the locations, and the mean is 0.0057, because this times we are talking about the concentration of heavy metals in them. So we are looking at the concentration of Nike across the three locations. I'm just kind of using it to divide the amount by accumulating in the organisms. So across the location. So now this is how it's done. For Suguru, you target. Take for instance now. This is Nike in Suguru. Nike in Suguru is 0.0025. So you use that to divide the concentrations of Nike in Suguru. That is all the organisms in sugar for the amount they absorbed in Nike, you use the mean concentration for Nike in sugar here to divide everything. Now, if you do that calculations right now, you get this 0.1.12. So that's how you just calculate for each. That's how you calculate it. I put the formula there, but it's not displaying on my phone. But that's how you do it. Just take for each locations, the concentration of each heavy metals across the locations to divide the parameters of the organisms at each location. Okay. So moving on to the result discussions. It's straightforward. When you read that, you just get what is there. So this is the bioaccumulation level. I've told you how all this I got in already. Just take the values across each locations. The values across each location. So we're going to take the values across each locations here. 0.0025, 0.0029 across that location, that level of sugar of the heavy metals, to multiply all the organisms that are bioaccumulated in Nike across the same pattern here. For each of the organisms, just take that quantity of water to divide all the amount that was bioaccumulated in sugar alone. So that's how you do that. So when you get that, you get those values that bioaccumulated here. You get all those values as your bioaccumulation figure. Then you also do the same for the sediment too. For the sediment also. Now this are the bar charts for the bioaccumulation, showing the organisms and the 8 metals in them. And you can see at a glance that copper has the highest concentrations in them all. Same thing goes for all the organisms, the samples that was analyzed. So, and those samples were analyzed based on location. You can see Makoko sediment, Shogunro sediment, Ebute sediment, water. This the first three graphs are for water. Then the next three graphs, Makoko, is Songuro, Makoko, and Ebute. So now this is the correlation analysis for the water, which is the last part towards the risk assessment. It says a correlation analysis between the location, the species, and heavy metals. And here is what happened. If you look closely, you did see some values having, you see the one correlations. This one is telling you that there's a perfect correlations. But however, you need to determine the amount of correlations that is in them. So between the species and the locations, the correlation is weak. And how do I know that? Is from 0.3 downward is a weak correlation. 0.3 downward is a weak correlation. Then a 0.3 to 0.7 is a moderate correlation or a medium correlation. And a 0.7 to 1 is a high correlation, or you say a strong correlation. So how I know that this is a weak correlation is because it's 0.092. So it's a weak correlation. And then if you look at Nike to the location, it's 0.2, which is also a weak correlation. So if you also look across, move across towards correlating lead, with chromium and all that, you did see each value. So all you need to do is to trace each values, compare with the horizontal to see the correlation values. Now, if you also notice, the some are minus, some are positive. If you read the statement, if you like, some are positive, some are negative. What it means is simply telling you the direction of the correlation. So if it's negative, that means as say as the vertical axis, which is the one at back axis, let's say chromium, as chromium is increasing, then the species say the species growth is being affected. It's not well, as it's being poisoned. The more the poison, the less growth. We can deduce that, because the relationship is going to be negative on the species. That's what it's telling you there. If there's a graph to be plot, if a graph is supposed to be plot between lead and species, you did see it did come down slants, like it slants something. And those with positive is telling you that it's going to start from the origin and increase upward. So that means increase in cadmium across. It's also increases across the location. That is what it's telling you. It's just basically telling you the relationship, or it's telling you the direction of the relationship. Is it negative? Is it positive? So how to say this right now between lead and the species is that the relationship is negative. The correlation is weak because it's 0.1. All right. So that is how you say it. So negative relationship and weak correlation. So the another thing you need to take conversant with is the asterisks. Some has 1 asterisk, some has 2 asterisks. What it's telling you is the correlation significance level. When if there's 2 asterisks on them, that means the correlation is significant even at 0.01. That is as low as you can talk about. So that means the correlation, the significant differences between locations. When we say significant difference, that is we are just comparing a mean of one location to another. Take for instance, one location is 0.56 and the second location is 0.002. Now, if you look at the gap between the two, how big is the gap? Is the gap between the two greater than 0.05, or is not greater than 0.05? If it's greater than 0.05, that means there's a significant difference. If it's not greater than 0.05, that means there's no significant difference. And at the same time, if the value between the pair of them is as big as 0.01, then it's a significant difference among them at 0.01 level. But if the difference between them is not up to that, maybe the distance between them is, so maybe they are very close, because the closer this, you don't have any significant difference when the values are very close at close range. You only have reason to discuss significant difference between concentrations of different locations when the distance between them is wide. Do you understand? So that's when we talk about significant difference. That is, the space between the two of them is as big as 0.01. You know, what we are concerned about is that there is no significant difference among them. That is the hypothesis. The hypothesis states that there is no significant difference, but you will have no enough statistical information to deny the hypothesis if there is a significant difference among them. But your hypothesis is stating that there is no significant difference among them, that the two of them are correlated. So if there is a significant difference among the locations, it will be flagged. And that is what is happening here. So it's basically telling you that there is a significant difference of cadmiums between cadmiums and Nike at 0.005. So that's just it. Then in the risk assessment calculations, some values being used, the metal concentration in the fish were transformed into dry weight, which is very, very important. If you wanted to calculate risk assessment, the values should be in dry weight. Your values are in wet weight, but I don't want to believe the man did any calculations as concerning converting into wet weight to dry weight. I don't think it does that. If it does, probably would have told you. But since it doesn't, then we can just adopt a conversion factor value, and then as been stated, by applying an average concentration factor of 4.8 according to KH Rind et al. That's 2024. What 4.8 means, that's 480% conversion factor. Some might use, depends on you though. You might try to use 20%, you might try to use 50% just to convert, just as to use as your conversion factor, just to convert, because in height risk assessment you are kind of calculating a life span of a man who has been poisoned with heavy metal all this long, and we'll see what kind of effect it's going to happen to a kind of person. And so there are formulas which are rightly stated in it, but it's not really displayed because I'm using smartphone. But when you transfer the document into your system, you do get the information and the formulas right correctly. So if you want to now, and you can also check the journals, which was the journals that you have shared sometimes ago. If you look at how the estimated daily intake was calculated, you did see too that they said the metal concentrations in the fish muscles was transformed into dry weight by applying an average concentration factor of 4.8. He also quoted an author that also did the similar thing, so I adopt that method from him. And then if you use in DFT, you can see the formula for the EDI. He calculated the concentration of the metals multiplied by the weight of the fish ingested, that is the IR, then the body weight. So those are the assumption values of his. He used 70 as the injection rate. Then he used for the weight of the fish, for the body weight of a man who has been consuming the fish, was considered 60. And this is the average fish consumption, which is 70 grams here. So now if you come to the table here, you just see the values that I also updated for this work. The injection rate, I used 100 milligram per day. Dry weight, the meaning of the W there is dry weight calculations. And then another thing you should also note, in case you have been asked, this risk assessment was calculated for adults. If you look, you see say calculated for adults, and even in here too, the one you shared, it was calculated for Pakistani men, so which is also for adults. And then if you take this formula, the formula of total hazard and target hazard quotient, and you substitute these values in it, you substitute all these values correctly, you did use it to calculate the target hazard quotient here for each heavy metals. So how the risk assessment was calculated was to take one organisms from the bottom feeders in one location, like 3 specific kind of organisms of different feeders: the bottom feeders, the column feeder, the surface feeder, as shown. Calculate the risk assessment, and of course you've seen the formula of how to calculate the estimated daily intake, which is the concentrations of heavy metals of Nike. Don't forget it has been converted. So if you want to do this right now, all you need to do is to take the value of Nike here in the concentration. Don't go to bioaccumulation, go to concentrations of the organism. Concentrations here, concentration of heavy metals in the aquatic organisms. Here, this is a bottom feeder 0.003. Then multiply this by the conversion factor to dry weight, which is 4.8. If you multiply this times 4.8, you will get your dry weight amount. which is your concentration, your metal concentration. So your metal concentration from there, you can then multiply it. You will then multiply it by your injection rate. Injection rate is 100 milligram. Then you divide it by the body weight, which is 70. That will give you the EDI. So you do the same for each metals of these particular organisms. So, and if you want to do the total hazard quotient, the formula is right there. So all you need to do is to substitute. Use the reference dose. The reference dose was gotten from Meltic, and as I write this there, the reference dose for heavy metals adopted for this research, milligram per kilogram source, is in Meltic et al. 2023, which I've also shared you the link before. So this is how it. So, and the reference dose that was used for this accurate assessment was the injection rate. So the inhalation, there's a 3 ways by which one can have reference dose is calculated actually. For EDI, most researchers use the inhalation alone, which is what the one you shared here used. They use inhalation, and how to get that is in the fish. You don't, even if there's bioaccumulation in the gills, livers, and muscles, you are not concerned about them because man don't eat gills. You rarely say you wanted to feed on fish gills or fish liver. What you want is fish muscles. And then what they basically do after this has been converted, what they have there is 1.68. So for 1.68 substituted here, MC, that's one, MC is 1.68, and high IRO, which is 70 kilogram, EF, which is the exposure frequency. Some researchers believe that you don't get exposed to soil every day, but here this man, the owner of the researcher, like says it's 365, but the one I used is 350, which might be true, especially for adults. Most times adults don't play with sand compared to children. And so if you multiplied the free exposure frequency times the duration of exposure, here they use 65, but I use 24. It's actually flexible and depends on you based on what researchers have been doing over the years. Conversion factor, I adopted this value 0.208. They multiply by 10 raised to power minus 3 divided by the reference dose, which are right there, multiplied by the body weight. And the body weight that was used here is 60 kg, which is rightly here, with an average body weight of 60 kg. And then the average exposure time. Here they use 10,950 days, but I use different values. I use 8,760 days for non-carcinogenic, because the calculation risks you are doing, all those words are very important when you are discussing them, that you are calculating for non-carcinogenic, because there's also a way to also calculate for carcinogenic. So this is not causing a cancer, so it's just a carcinogenic calculation. And then yeah, so you get the values for each total hazard content, and to get your hazard index, you simply add the total hazard quotient. The formula is there too, or you can just simply view from here. Hazard quotient measures the risk associated with multiple metals present in a contaminated food, and is calculated as follows. So hazard quotient is equal to the total target hazard quotient. That is, hazard index is calculated by summation of the total of the target hazard quotient. And how you do that is to add 2.05 times 10 raised to the power minus 5 plus 2.96 times 10 raised to the power minus 4. You know, if you do your math, then you did get the summation of everything we give you. What we have here is 0.0 0.02. So, and if you look at them, or you did see, if hazard quotient, if it's equals to 1, that means there's risk. If it's less than 1, there is no risk. So basically you can just look in a glance by saying that there is no risk at all on the men feeding on those fish, both the bottom feeders. Though there's bar accumulations, but the bar accumulation level is still at minimal level. If I'm comparing to the reference dose, you can still see that if man take all those things, though the level at which the concentration is there, but it's not significant to the point of hazard, So, and you can see the highest there is just 0.003, which is even the bottom feeders at Makoko at Shoguru having 0.002. So, which is also correlating with what they have here in Pakistan. If you look at Pakistan, all their hazard content still, none of them is up to 1. None of them is up to 1. So it kind of says, so the result was also kind of being discussed that there was not a hazard. So look at the way it was. Look at the way they kind of discussed the result here. So it says the strinta exhibit a higher concentration of heavy metals than both column dwellers and surface feeder fish. Also noting in their research, Jinga et al. Also noted in their research that Damsar fishes display a greater bioaccumulations of heavy metals. So compared to pelagic and bentopelagic fishes in Dongting Lake, China, aligned with the result of our studies. Additionally, by Assant et al., reported significant elevated levels of heavy metals in damsel fishes in their observations, bioavailabilities of heavy metals and sediments, and the suspensions of events. So the researchers kind of reported that though there is no significant threat at all, but he kind of discussed here in the hazard index. It says the value from the current study is below 1, indicating that the fish are safe for consumption. However, the hazard index values obtained from Marigala, which is the bottom feeders, was 0.82, which is close to the standard limit. So if contaminations or pollutions continue to increase at the current rate, it may exceed 1. So our results consistent with those of Woods et al. Who founded lower reference dose for heavy metals in pelagic, bentopelagics and damsel fishes. So that's how you discuss your results and you arrive in your conclusion. So, of course, what you've done also is, I think there are heavy metals that have once been analyzed. If not in all locations, I think I've seen the one of Makoko before. So you also just need to do is to get some journals who aligned with yours, or even though you have some who were against yours by saying there's a hazard, you can kind of say, okay, now this is the interval years for which that has been done. So you can kind of say probably the amount of pollution into that water has been reduced, and there have been a treatment to that water that have caused a reduction in heavy metal such that the fishes from those places can actually be consumed by men. And of course, we've known Makoko for a place where people fish a lot, and in fact for commercial purposes. So we are actually in line. So your research is perfectly fine, and there is no reason to be scared of that. The features gotten from makoko to the commercial basements are in any way and poisonous for men's consumptions. So this is a lovely data, and see you in the future. Bye.